Welcome back to the channel. In the previous video I have explained how the standby voltages on a motherboard must be created in the correct sequence to get a stable standby state. In the standby state, the motherboard is waiting for an event to trigger the power on sequence. This event is triggered by pressing the power button. In this video I will analyze the full startup sequence when you press the power button, which voltages and signals needs to be created in which order. In the description below you can find the playlist with all the videos about the standby and startup sequence in PC motherboards. If you have gained any value from this guide, consider giving it a like. It helped me to grow the channel and create more content that you enjoy. And do not forget to subscribe to the channel for more in-depth analysis like this one. So let's start. In the previous video I've explained how the RTC circuit gets its power. In the standby sequence, all these voltages and signals has to be created. So when you look at the standby state, all those signals has to be in the correct state. Eventually, there is one signal that has to be created. That is the resume reset signal. And this signal has to be high in the standby state. The motherboard is now waiting for an event to start the power on sequence. In the power on sequence, these are the voltages and signals that has to be created in the power on state. This is a standby state, and now we have to look at the power on state. So eventually all these signals has to be in the correct state. To start the power on sequence, we are waiting for an event, and this event will be pressing the power button. This power button will create a pulse, and that will be the signal to start the power on sequence. In area 14, the front panel jumpers are located. On these jumpers you can connect switches like the reset switch and the power switch. So in area 14 we saw the jumpers, so these are the jumpers. And on the power switch pins, the minus and the plus pin, we have to connect this power button. In the previous video you saw how we created the SuperIO 3.3 volts. It derives from the 5 volt standby voltage from the ATX power supply. This is the 3.3 volt that was created in the standby sequence. This is the pull-up resistor. It will pull this power button in signal to high. When the power button is not pressed, this signal will stay high because of this pull-up resistor. So it will be around the 3.3 volts. And when you press the power button, it will short this signal line to ground that will create a pulse. The 3.3 volt will go to 0 volts and back to 3.3 volts. So what will happen? We have a 3.3 volt at this signal line. In the standby state, this signal line is high. And when you want to power it on, it will go from high to low to high, high, low to high. And this button signal will go to the SuperIO chip. These are the jumpers for the front panel. And at these two pins we connect the power switch. So this is the positive line and this is ground. When you press the power button, it will short the positive line to ground. That will create a pulse on this power button in signal. And this signal will go to the SuperIO chip. This is the pull-up resistor that will pull up this power button in signal to 3.3 volts. The SuperIO chip is listening to this power button signal. And when the signal arrives, it will start the power on sequence. When you press the power button, this power button in signal goes into the SuperIO chip. This signal power button active low will go low. And this signal travels to the PCH chip. The difference is when you press the power button, it will go from high, low, back to high. And the signal that is sent to the PCH will go from high to low. So again, this is the SuperIO chip. The power button signal goes into this pin. The SuperIO will send a signal that will go from high to low to the PCH. The power button active low signal that comes from the SuperIO chip, that is low. It will go to the PCH. What will happen is that the power button active low signal is default at 3.3 volt. So in the standby state it's high, and when you power it on it will go to low. And this signal comes from the SuperIO and it goes to the PCH. This is the PCH and the signal can be found near the PCH in one of those resistors. So at this resistor you can measure this power button active low signal. When we press the power button, it created a pulse. This pulse has been sent to the SuperIO chip, and from the SuperIO chip, this pulse is sent to the PCH. PCH will now send two sleep states signals, that is 4 and 3, so sleep state 4 and sleep state 3. Not all motherboards implement the sleep state 5. So these two signals are active low, and these signals will be sent from the PCH back to the Super I/O chip. So in the power on state, these 2 or 3 signals has to be high. The sleep state signals 3 and 4 can be found near the PCH chip. In power on sequence number 17, the PCH has to create 2 signals and will be sent to the Super I/O chip, that is sleep state S3 and sleep state S4. And this signal will go from low to high. The output resistance of these 2 signals is higher than 30 kilo ohms. The sleep state signals S3 and S4 are signals that are related to power states. These signals are generated or managed by this platform controller hub. This signal indicates whether the system is in the S3 state, and the S3 state is also known as a suspend to RAM state. This is a low power mode where most of the system components are powered down, but the random access memory is kept powered to retain the data. When the signal is low, it indicates that the system is in an S3 state or the sleep state. When the signal is high, then the signal is not in a suspend to RAM state. The S4 state is also known as a suspend to RAM disk. It's a lower power mode where the system state is saved to the disk, and almost all components, including the RAM, are powered down. These 2 signals will drive different components to power down unnecessary parts of the system, such as the RAM and other connected peripherals. So it will power on and power off different components in different states, so in the sleep state or in power on state. In power on sequence 17, these 2 signals are in a standby state low, and when you press the power button, they eventually have to go high. The signal comes from the PCH and it will go to the Super I/O chip. So this is the PCH, and near the PCH we have 2 resistors, and on those resistors you can measure the sleep 4 and sleep 5 state. This is a Super I/O chip, and those 2 signals that comes from the PCH will eventually go to the Super I/O chip. This is a Super I/O chip, so on pin 64 this sleep state S3 comes from the PCH, and the other signal goes to pin 84, and that is the sleep S4 signal. When the power button is pressed and the signal goes from the Super I/O chip to the PCH will send the sleep state 4 and 3 back to the Super I/O chip. When the Super I/O chip receives those 2 signals that are high at power on state, the Super I/O chip will send a power supply on active low signal back to the power supply. Default, the power supply active low signal is at 5 volts, so it's high. But when the Super I/O chip wants to turn the power supply on, it will pull this signal to ground. The power supply on signal can be found near the Super I/O chip, and this signal will be sent to the 24-pin ATX power connector. And from this connector, the signal goes to the ATX power supply. In power sequence 18, the Super I/O received the 2 sleep states, the S3 and the S4. When the Super I/O chip receives those 2 signals, it will send a signal back to the ATX power supply to turn it on. The signal is called power supply on, active low. When the signal is pulled to ground, it will go to the 24-pin ATX power connector. It will go to the ATX power supply. Because the signal line is pulled to ground, the power supply will activate or turn on all those voltages. The power supply on signal is used by the motherboard to control when the power supply should be turned on or off. When the signal is pulled to ground, the power supply turns on and provides power to the system, so all these voltages will be turned on. When the signal goes back high, it will turn off the power supply and only the 5 volt standby voltage will be present, so this voltage will only be present. This is the 24-pin power connector, and the power supply on pin will go from 5 volt to ground. This signal line will trigger the ATX power supply to start generating all the powers at its output, like the 12 volt, 5 volt and 3.3 volt. In power sequence 18, in standby mode, this voltage has to be high, so it has to be 5 volt. And in the power on state, when you press the power button, it should go to 0 volts, so it will be shorted to ground. The signal comes from the Super I/O chip and it will go to the ATX power supply. The power supply active low signal line comes from the Super I/O chip and it will go to the 24-pin ATX connector. When the ATX power supply receives this power supply on active low signal, so it's pulled to ground, it will start generating all the voltages at the output of this 24-pin ATX power connector. Also, the plus 12 volt will be generated for the CPU, so this is a separate connector, the CPU connector. On this connector you can measure the plus 12 volt, and this 12 volt will be converted into a VCORE of plus minus 1 volt. In the power on state, the current draw of the motherboard can be between 1 to 8 amps. And that's because the CPU is turned on and the CPU needs a lot of current. On the 24-pin connector you can find all the voltages that will go from low to high at the output. And also the minus 12 volt is used for the audio amplifier, so this one, min 12 volt, is only used for the audio amplifier. When all these voltages are generated successfully, the power supply will send an ATX power OK signal back to the motherboard. This is the 8-pin CPU connector, so the plus 12 volt will be generated and this 12 volt will be converted into a VCORE of plus minus 1 volt. So again, if all the voltages are generated successfully, there's a power OK signal. The power OK signal tells the motherboard that the output voltages from the power supply are stable and within the correct range. When the power supply turns on, it takes a moment to stabilize the output voltages, such as the 12 volt, 5 volt and the 3.3 volt. During this stabilization time, the power OK signal is held low. Once the voltages are stable, the power supply sets the power OK signal to high. In power sequence 19, the ATX power OK signal goes from a low state to a high state, so it will go from 0 volts to plus 5 volt, indicating that all the voltages that needs to be generated are OK. And this signal will come from the ATX power supply through this 24-pin ATX connector, and at this resistor you can measure this ATX power OK signal. And this power OK signal will go to the SuperIO chip at this pin. And the resistance at this pin is higher than 1 kilo ohm. When the ATX power supply has informed the SuperIO chip that the power creation of the power on voltages are OK, and then the SuperIO chip will check if the internal voltages are present, and it will send a power OK signal back to the PCH. This system power OK signal has different names, so most commonly used is the system power OK. It is also called chip power good or power OK. Power OK signal that comes from the SuperIO chip is generated in this chip, and it will go to the PCH. In power sequence 20, the SuperIO chip received the ATX power OK signal from the PSU, saying that all the power on voltages are OK. After that, the SuperIO chip will send a chip power good, also known as a system power OK or power OK signal, back to the PCH. And this signal goes from low to high. The resistance of this power OK signal is higher than 30 ohms. The power OK signal can be called system power OK, or chip power good, SuperIO power OK, or just power OK. Eventually this signal has to be generated in the SuperIO chip and it will go to the PCH. Power OK is a signal to indicate that all the internal power rails are stable and within the correct specifications. It is closely related to the ATX power OK signal that is provided by the PSU. Unlike the ATX power OK signal, which comes directly from the PSU and signals that the main power is stable, this power OK signal is generated by this SuperIO chip. The power OK signal is often part of a handshaking protocol between the motherboard and the PSU. So after receiving the ATX power OK signal from the PSU, the motherboard performs additional checks on the internal voltage regulators, power delivery circuits and other subsystems. Once all these checks passes, the SuperIO chip will send a power OK signal back to the PCH. The PCH relies on this signal to continue the power sequence. Power OK signal can be found near this SuperIO chip, in this case on pin 81. In power sequence 20, the power OK signal has to go high, so in standby mode it's 0 volts, in the power on mode it goes to 3.3 volts. The signal comes from the SuperIO chip and will go into the PCH chip. On this motherboard you can find the power OK signal at this transistor or MOSFET, and it's located near the PCH chip. Basically the power OK signal will create the voltage for the clock signal and the voltage for the data lines for the serial communication. In power sequence 20, the serial clock voltage and the data voltage has to go high at 3.3 volts. On this motherboard, at these two MOSFETs, you can find the serial data and the serial clock signals. When the internal voltages in the SPIO chip are stable and generated OK, then the signal will go to the PCH. When the PCH receives this signal, it will continue to the next sequence. Next, the PCH will generate a 24 MHz clock signal, and this clock signal is not present in the standby state. In the power on state, the PCH clock has to generate a clock signal of 24 MHz. When the internal voltages are OK and stable at the SPIO chip, it will send the system OK signal to the PCH. When the PCH receives that signal, it will start generating a PCH clock signal of 24 MHz. In power sequence 21, the PCH clock signal has to be generated of 24 MHz. So in the standby state, there is no signal created, and in the power on state, the 24 MHz signal will be generated. When the signal comes from the motherboard, it will go to the PCH. This is the PCH chipset, and at these pins, the 24 MHz clock signal will be generated. The PCH clock signal is the timing reference that synchronizes data transfer between the PCH and other components that are connected to the PCH. This is the chipset, and near the chipset you can find a rectangular squared crystal oscillator, and this oscillator will generate a 24 MHz clock signal. So you can measure the signal with an oscilloscope at this capacitor. Then you can measure the input and output of this crystal oscillator. So with an oscilloscope you can see a waveform. When the PCH clock frequency of 24 MHz is created in the power on state, in this sequence, the USB power sequence, we have to determine what will be the destination voltage of this 5 volt. So this destination voltage can come from the plus 5 volt standby voltage or the 5 volt VCC voltage when the ATX power supply is turned on. Depending on the sleep state 3 and 4 and also the BIOS settings, this USB power controller will determine if the plus 5 volt is generated for the USB. This USB power controller will determine what will be the plus 5 volt for the rear USB connectors and the front USB connectors. Depending on the sleep state 3 and 4, it will deliver power to the front and the rear USB ports. And the plus 5 volt voltage can come from the ATX power supply when it's turned on, that is the VCC5, or it can come from the 5 volt standby voltage. If you want the USB ports to be active in the standby mode, if you set this option on in the BIOS settings, this controller will send a signal to generate the plus 5 volt from the 5 volt standby voltage regulator. In power sequence 22, this controller will select which will be the source voltage for this plus 5 volt USB. So the source voltage can be the 5 volt standby voltage or the VCC 5 volt when you turn on the ATX power supply. To determine what will be the source voltage, this controller relies on these three signals. So the sleep state 3, sleep state 4 and also the USB mode. Depending on this mode, it will determine the destination voltage. And also if you have turned on the setting in the BIOS to turn on the USB ports in standby mode, depending on this mode, it will send the 5 volt standby drive signal to the USB voltage regulator to get the 5 volt from the 5 volt standby voltage. In power sequence 22, we have to create the 5 volt for the USB connectors. In standby state, this voltage will not be generated unless you turn it on in your BIOS. In the power on state, this voltage will go from 0 volts to 5 volt. To generate this voltage, it depends on the sleep state 3, 4 and the USB mode. So these signals will determine how to generate this plus 5 volt. And this is the USB power control chip. And depending on the USB mode, sleep state 3 and sleep state 4, it will determine which signal will go to the USB voltage regulators. When this signal is sent, it will get its 5 volt from the 5 volt VCC from the ATX power supply. And when this signal is sent, it will get its 5 volt from the 5 volt standby voltage. The depending on which signal comes from the USB controller, it will generate the plus 5 volt for the USB connectors. If the USB voltage of 5 volt has to be generated from the standby voltage, then this MOSFET is turned on and it will get its voltage from the ATX 5 volt standby voltage. And when this signal, the 5 volt drive USB signal, arrives, it will get its voltage from the VCC 5 volt from the ATX power supply. The difference between those two MOSFET is, in a standby state, this MOSFET can only deliver a low current at the output. And when the power supply is turned on, this VCC5 will go through this MOSFET, and this MOSFET is used to deliver a high current to the output. A small MOSFET for the low current output and a high MOSFET for the high current output. This is a small MOSFET and it can only handle small currents at the output. This is the bigger MOSFET and this can handle higher current. And basically, at this fuse, the 5 volt USB power will be present. In power sequence 22, the rear USB power will generate a voltage of plus 5 volt for the USB connectors. In the standby state, the USB connectors do not have any voltage. And in the power on state, it will go from 0 volts to 5 volts. And it depends on these three signals: the USB mode, sleep state 3 and sleep state 4. For the front USB power circuit, we have the same layout. This is the small MOSFET, this is the bigger MOSFET. This bigger MOSFET will be turned on in the power on state, and this smaller MOSFET will be turned on in the standby state. This is the USB front panel, and at this pin the 5 volt USB power will be generated. The resistance at the output is higher than 1 kilo ohm. If the USB power of 5 volt is present at the power on state, the next sequence will be to generate the 5 volt dim voltage rail. The 5 volt dim voltage is a voltage of 5 volt and it will be used by the RAM circuit and the dim slot. So all these voltage rails derives from the 5 volt dim. If the 5 volt dim voltage is not present, all the child voltages will not be created. In the power on state, the 5 volt dim voltage has to be 5 volt. There has to be 2.5 volt present. The VCC for the DDR RAM modules has to be present. And also the VTT for the RAM modules has to be present. The 5 volt dim circuit is located in area 18 and that is near the RAM slots. In power sequence 23 we have to create a 5 volt dim voltage rail. It's a voltage of 5 volt. In the standby state it is low, it's 0 volt. And in the power on state it has to go from 0 volts to 5 volt. The sleep state 3 and 4 are responsible for generating the plus 5 volt for this 5 volt dim voltage rail. This is the 5 volt dim controller, and depending on the sleep state 3 and 4 and the mode, it will determine where this 5 volt comes from. So this 5 volt can come from the ATX 5 volt standby voltage and also from the VCC 5 pin from the ATX power supply when its power supply is turned on. Depending on sleep state 3 and 4, it will send a 5 volt standby drive signal to this MOSFET, and in the power on state it will send a 5 volt VCC drive signal to this bigger MOSFET. So the destination voltage can come from the 5 volt standby voltage or from the 5 volt VCC, and this comes from the ATX power supply when you turn it on. The output of this 5 volt dim voltage rail is higher than 1 kilo ohms and it has to transition from 0 volts to plus 5 volt. The 5 volt dim rail does not power the actual memory chips directly, but it is used as the source voltage to create different RAM related voltages that will go to the dim slots. Basically all the voltages that are RAM related will derive from this plus 5 volt dim. This is the 5 volt dim controller, and this is the sleep state S3 and sleep state S4 on those two pins. Depending on the state of these two signals, it will send a signal to the smaller MOSFET or the bigger MOSFET to determine what will be the source voltage of 5 volt. And this is the output. Eventually the 5 volt dim voltage of 5 volt has to be created and the output is higher than 1 kilo ohms. When the 5 volt dim is present at the power on state, and the next power sequence is to create a VPP voltage of 2.5 volt, and this voltage is derived from the 5 volt dim. Before creating the VPP 2.5 volt, we have to create a enable signal to the voltage regulator that will create the VPP 2.5 volt. In power sequence 24, we have to create a VPP enable signal that will go to the voltage regulator to create the VPP 2.5 volt. The VPP enable signal is the enable signal to start generating the VPP 2.5 voltage. The VPP stands for voltage for pump power. It's a separate voltage rail designed to provide a high voltage specifically for the word line drivers inside the DRAM. Word line drivers are responsible for activating rows in the memory array during the read and write operations. This VPP enable signal has a voltage of 1.6 volt. In the standby mode, this signal is not present, and in the power on mode, it has to go from 0 volts up to 1.6 volt. The sleep state S4 and the SIO VPP enable signal will enable this voltage. So these two signals will determine if this enable voltage is present. In this chip there are two MOSFETs located. This is one MOSFET and this is second MOSFET. This chip will send the VPP enable signal of 1.6 volt. It goes from 0 volts to 1.6 volt and the output is higher than 1 kilo ohms. In power sequence 24 we have to create the VPP 2.5 volt. In the standby state this voltage is not present, and in the power on state it has to go from 0 volts up to 2.5 volt. This is the buck converter, so the enable signal goes into this enable pin. The 5 volt DIMM VPP is the power supply for this chip. When this enable signal is high, it will turn on this chip and it will start generating the 2.5 volt. And this voltage goes to the DDR4 memory. When this buck regulator is functioning correctly, it will create a power good signal called VPP VR power good. And this power good signal will go to the voltage regulator to create the voltage for the DDR4 memory. This is the buck regulator. When this regulator is powered on and the enable signal of 1.6 volt is present, it will turn on this regulator. It will start generating the 2.5 volt at the output. And if the 2.5 volt is generated correctly, it will create a power good signal that will go to the voltage regulator that will create the voltage for the DDR4 memory. This is a DIMM slot, and at these pin numbers you can find the VPP 2.5 volt. This is the DIMM connector, and the pins marked in yellow are the VPP 2.5 volt rails. The next step is to create the VCC DDR voltage, and VCC DDR is the main power supply for the RAM modules. This mainboard supports DDR4 memory, and DDR4 memory has a main power supply of 1.2 volts. In area 20, the main power supply of 1.2 volt for the DDR4 RAM modules is created. This power supply will deliver 1.2 volt to all the RAM modules that are connected in these DIMM slots. This is the buck converter that will create the 1.2 volt that will be used by the DDR RAM modules. This chip needs a power supply of 5 volt that comes from a 5 volt DIMM power rail. To turn on this buck converter, it needs an enable signal, and this enable signal comes from a 2.5 volt from the VPP 2.5 power rail. When this voltage is present, it will generate an enable signal to turn this buck converter on. This buck converter will drive the upper gate and the lower gate of two MOSFETs, and those MOSFETs are connected to the 5 volt DIMM power rail. When the voltage of 1.2 volt at the output is created successfully, it will create a feedback signal that will go back into this buck converter to regulate the output voltage. In power sequence 25, we have to create the main power supply for the RAM modules of 1.2 volts. In standby state, this voltage rail is low, and in the power on state it has to go from 0 volts up to 1.2 volts. When the sleep S4 signal and the power rail of 5 volt is present, then this buck converter can generate the 1.2 volts. VCC DDR refers to the main power supply provided to the DDR memory modules on the motherboard. It is the main voltage rail that powers the memory chips themselves. The specific voltage level of this VCC DDR depends on the type of DDR memory that is used. For DDR1 it operates at 2.5 volt, for DDR2 it operates at 1.8 volt, DDR3 operates at 1.5 volt, DDR4 operates at 1.2 volts and DDR5 operates at 1.1 volt. This is the buck converter that will create 1.2 volt for the main power supply for the DDR4 RAM modules. This chip needs 5 volt to operate, and it needs an enable signal of 2.5 volt that comes from the SuperIO chip and the VPP 2.5 volt power rail. Then the buck converter will drive the high side MOSFET and the low side MOSFET. The high side MOSFET is connected to the plus 5 volt DIMM voltage, and that will be used to generate the 1.2 volt. This is the high side MOSFET, this is the low side MOSFET. The drive signal for the high side MOSFET comes from the buck converter and also for the low side MOSFET. And the high side MOSFET is connected to the 5 volt DIMM voltage rail, and the 5 volt will be chopped into 1.2 volt that will be used by the RAM4 modules. The output resistance is higher than 280 ohms. This is a low side MOSFET and this is the high side MOSFET. So the high side MOSFET is connected to the plus 5 volt DIMM voltage rail, so 5 volt will be chopped into 1.2 volt, and this voltage can be measured at this coil. The main power supply of 1.2 volt that is needed for the DDR4 modules that are connected into these DIMM slots. You can measure the 1.2 volt at all the pins that are marked in yellow. When the power supply for the DDR4 RAM modules is created, the next step is to create a voltage for the CPU. And the next voltage is called VCCSA. This power rail is used by the CPU, and the purpose of this voltage rail is to provide power to a subsystem in the CPU. What it exactly does, I don't know, but the CPU needs this voltage. The enable signal to create this VCCSA, this voltage for the CPU is created in this region. In power sequence 26, the enable signal VCCFROC enable signal is generated. This enable signal is used to create the voltage rail VCCFROC. This enable signal depends on two signals, the sleep S3 state and the DDR power good signal. This power good signal comes from the previous sequence. When the DDR power good signal is high and the state of the sleep state S3 is not in a sleep state, so it's also high, then this enable signal will be present. So it goes from low in the standby state to high in the power on state. And the output voltage is around 3 volts. On this motherboard, these signals are present on this location near the M.2 slots. And the output of 3 volt is used to create the power rail VCCFROC. So this is a power rail for the CPU and it is used to power some subsystem in the CPU. In the next step, this voltage regulator will create 1.2 volts for the VCCSFROC power rail, and this power rail will go to the CPU. The output resistance is higher than 1 kilo ohms. When this enable signal is present, it will turn on this voltage regulator, and this voltage regulator will generate the 1.2 volts. When these signals are high, it will turn on this voltage regulator, and it will start generating the 1.2 volts. This chip is the voltage regulator, and at this output the 1.2 volt is created and it will go to the CPU. When the power rail SFCOC is created, the next step is to create the VTT DDR voltage rail, and VTT stands for termination voltage, and it is used by the memory. And this voltage is the power supply divided by 2. So if the power supply is 1.2 volts, this VTT voltage would be 0.6 volt. And this voltage has to go high. In region 22, the termination voltage that will go to the RAM modules is created. This voltage is the VCC DDR power supply, so that is 1.2 volt divided by 2. So the VTT voltage that will go to the RAM modules is 0.6 volt. In region 27, we have to create the VTT DDR voltage rail, that is 0.6 volt. VTT DDR stands for termination voltage, and this voltage is used for terminating the data lines DQ for DDR memory. This voltage helps to prevent signal reflections, especially at high frequencies. Signal reflections can cause data errors, so a proper termination voltage is crucial. The termination voltage of 0.6 volt will go to the RAM modules. This is the voltage regulator that will create the 0.6 volts, and this voltage regulator depends on two enable signals. The sleep state S3 has to be high, And this enable signal, the DDR VTT control signal, comes from the CPU. When these two enable signals are present and the input power supply is also present, it will start generating the 0.6 volt. And the output resistance is higher than 1 kilo ohms. So in power sequence 27, we have to create a termination voltage of 0.6 volt. It will go to the RAM modules. In standby state, the voltage is low, so 0 volts. And in the power on state, it will go from 0 volts up to 0.6 volts. And to create this voltage at the output, it depends on these signals. And this is the voltage regulator, and at the output, the 0.6 volt will be created. And the enable signal DDR VTT control comes from this CPU. And the second enable signal comes from the sleep state S3, and that has to be high. When the termination voltage of 0.6 volt is created, that goes to the RAM module. The next step is to create the CPU voltage VCCIO, and that is in power sequence 28. It has to go high in the power on state. In region 23, the VCCIO CPU voltage is created. In region 28, this is the buck controller. It will create 0.95 volt that will go to the CPU. And the CPU voltage rail is called VCCIO. VCCIO is a voltage of 0.9 volt. In a standby state, this voltage is not present. And in the power on state, it will go from 0 volts up to 0.95 volts. This voltage derives from the 12 volt. The 12 volt that comes from the ATX power supply will go to this buck controller. And this buck controller will regulate this voltage back to 0.95 volt. The enable signal derives also from the 12 volt, so if the 12 volt is present, it will go through this resistor. This is a voltage divider, and this enable voltage will go to this chip. The output resistance of this CPU voltage is higher than 50 ohms. So the VCCIO provides power to the integrated memory controller that is inside of the CPU, which handles the communication with the system's random access memory. This is the CPU, and near this CPU there is the buck controller, and this buck controller will start generating the 0.95 volt that will go to the CPU. And this is the CPU, so this voltage rail goes directly into the CPU. In power sequence 28, the VCCIO voltage has to be created. In the standby state, it's 0 volt, and in the power on state, this voltage goes from 0 volts up to 0.95 volt. And the 12 volt also creates the enable signal for the buck controller to create this voltage that will go to the CPU. These are the CPU pins on the main board, and all the pins marked in yellow are the VCCIO voltage rails. I couldn't find this voltage rail on my motherboard, so I will skip this sequence. So the next sequence, sequence number 29, is called VCCSA, and this is a voltage rail that will go to the CPU. And the SA stands for system agent. This voltage rail has to go high in the power on state. In area 24, we can find the VCCSA voltage, and this is the voltage that is needed by the CPU. In power sequence 29, we have to create the CPU voltage VCCSA. This is a voltage of 1.05 volts. In the standby state, this voltage is not present, and in the power on state, it will go from 0 volts up to 1.05 volt. This voltage will be created when the VCCSA enable signal is present at pin 7. This is the buck controller, and when this enable signal is present, and also the VCC is present to power this chip on, it will start generating the 1.05 volts. So the 12 volt from the ATX power supply will create this VCCSA enable signal. It will enable the chip, and this chip will start generating the 1.05 volts. The VCCSA enable signal depends on the VRM enable signal. So when this VRM enable signal is high, then this enable signal is present. The VCCSA is a system agent voltage, and this voltage is used in the CPU. This voltage is responsible for powering the system agent, which includes a number of components related to the system's memory controller, the PCIe controller, and display interfaces like the integrated graphics. So this voltage of 1.05 volt will go to the CPU. Near the CPU you can find the VRM enable signal and also the VCCSA enable signal at this chip. The output resistance of this VRM enable signal and the VCCSA enable signal is higher than 7 kilo ohms. Near the CPU, this is the buck controller. The buck controller is located near the CPU. The input is 12 volts. On pin 7, the VCCSA enable signal will be present. This buck controller will send a signal to the low gate MOSFET, also to the high gate MOSFET, and then the voltage of 1.05 volt will be created and it will go to the CPU. The drive signal to drive this high side MOSFET and the low side MOSFET comes from the buck controller. These two gate signals will go to the high side MOSFET and this one will go to the low side MOSFET. The buck controller will send signals to the high side MOSFET and the low side MOSFET. These two MOSFET will chop this 12 volt up to 1.05 volt and this voltage will go to the CPU. The output resistance is higher than 20 ohms. So again, this is the low side MOSFET, this is the high side MOSFET. These will chop the 12 volt into 1.05 volt. So at the output of this coil, you can find the 1.05 volt and the output resistance is higher than 20 ohms. And as you can see here, this voltage will go to the CPU. These are the CPU pairs that are located on the mainboard. And the pairs marked in yellow is the VCCSA voltage rail. This VCCSA will provide power into the CPU in the system agent part. Next, in power sequence 30, we have to create the power for the integrated graphics. That's the voltage GTX. I couldn't find this on the motherboard, so I cannot explain how this is created, but if it is present, it has to go high. The VCC GTX is a voltage rail that will provide power to the integrated GPU that is in the CPU processor. As you can see here, these are the power supply pins. I couldn't find where this was created. So in this case, I will skip this sequence. When these CPU voltages are created successfully, the next thing is that we want to create the core voltage for the CPU. Before creating the core voltage, the CPU has to communicate with the PWM phase driver in what kind of voltage the CPU needs. In these two power sequences, this communication is done by the CPU and the PWM phase drivers. So the SVID is known as a serial voltage identification. It is an interface protocol used between the CPU and the multi-phase PWM controller, which is responsible for generating this VCORE voltage. This is the core voltage required by the CPU, and this communication enables this voltage regulation. The CPU has to communicate with this PWM multi-phase driver controller to specify what kind of core voltage this CPU needs. So the SVID, the serial voltage identification, is a interface protocol used between the CPU and with this multi-phase PWM controller. This multi-phase PWM controller is responsible for generating the VCORE voltage that will be used by the CPU. The CPU uses the SVID data lines to inform the PWM controller about the specific voltage it needs. This is needed because the voltage requirements are different based on the CPU workload and power state, like idle, boost or high load scenarios. Based on the current state, it will inform the PWM controller what kind of voltage it needs. The SVID data lines enables a two-way communication, meaning the PWM controller can report status information back, like over voltage or under voltage condition, or over current events back to the CPU. So the PWM controller can send information back to the CPU. The SVID protocol uses three signals. First one is the clock signal, then we have the data signals, and there is an alert signal. So the clock signal provides the timing signal for communication between the CPU and the PWM controller. Then we have the data signals, which transfers voltage requests, power state commands and fault reports. And the third signal line is called alert active low. So the alert signal indicates that the PWM controller has information to report back to the CPU, such as a status update or a fault condition. This is the multi-phase PWM controller that will generate the VCORE voltage that will go to the CPU. And as you can see here, we have the three signal lines. So this is the SVID protocol. It has three signal lines. We have the data line, the alert line, and the clock line. And these three signal lines will go to the CPU, and it's a bi-directional communication. So the information will go between the CPU and this PWM controller. This is the PWM controller, and at pin 24, 25 and 26 we can see the clock pin, the alert pin and the data pin. It's located in this region. When the CPU has communicated with the PWM driver, it knows what kind of CPU core voltage it wants, and then it's time to send an enable signal to the VCORE controller that will generate the VCORE voltage. So VCORE has to go high, and it is the main power supply for the CPU. This is a CPU, and the VCORE, the main power supply for the CPU, is generated by these phase drivers. So these are 4 phases, and this controller will send the PWM signal to every phase to start generating the VCORE voltage, and it will go to the CPU. In power sequence 31, we need an enable signal that will go to the VRM controller to start generating the VCORE voltage of 1 volt. But to turn that controller on, we need an enable signal. So in power sequence 31, we need 1.6 volt in the power on state. In the power on state, it will go from 0 volts up to 1.6 volt. And this enable signal of 1.6 volt is created by the sleep S3 state. The sleep S3 state shouldn't be high, so it shouldn't be active. So this voltage has to be high, and because this voltage is high, the switch will not pull the VRM enable signal to ground. So the VRM enable will be high, and that will be 1.6 volt, and this will go to the buck controller. The output resistance of this enable signal is higher than 7 kilo ohms. So in this case, the enable signal depends on 2 signals, the VCCIO power good and the sleep state S3. Near the multi-phase PWM controllers, you see these 2 ICs. So this is a dual MOSFET in one package IC, and this is the same. The sleep state S3 enable signal is high, it will go to this pin. And the VCCIO power good signal that comes from this voltage rail will go to the male pin of this IC. When these 2 signals are present, it will create the VRM enable signal, and it creates it from the 12 volt ATX power supply. When the ATX power supply is turned on, it will create the 12 volt, and this 12 volt will be used to create the enable signal, the VRM enable signal, because of this voltage divider. So the VRM enable signal is 1.6 volt and it derives from the 12 volt. So this resistor divider will divide the voltage of 12 volt, and after that it creates the VRM enable signal of 1.6 volt, and that is because of this resistor divider. When the enable signal is created, it will go to the multi-phase PWM controller to create the VCORE. The created VCORE of 1 volt supplies power to the processor's cores, enabling the CPU to function and execute instructions. On pin 21 and 22, this is a serial communication between the PWM controller and the other parts of the circuit on the mainboard. So also in power sequence 31, we have to create the VCORE voltage of 1 volt. In the standby state, this voltage is not present, and in the power on state, it has to be generated up to 1.0 volts. And this PWM controller will start generating the VCORE when this enable signal is present. This is the PWM controller, and at these 2 resistors, the serial communication goes into the chip. When the VRM enable signal is high, this PWM controller will be turned on. The PWM controller also needs a power supply of 5 volt to operate. When the enable signal is present, it will start generating PWM signals. This PWM controller has 1, 2, 3, 4, 5 PWM signals that will go to the PWM driver chip, and the PWM driver chip will start generating a voltage. In power sequence 31, the PWM controller needs 5 volt to operate. It needs enable signals to start generating PWM signals. 4 PWM signals will go to the VCORE driver chip, and 1 PWM signal will go to the PWM driver chip for the VGT. I think this is the graphics driver. This chip is the multi-phase driver IC, and this chip receives a PWM signal from the multi-phase PWM controller. It will get its PWM signal at this pin. Then we have the enable signal to turn this PWM driver IC on. And this PWM driver IC also needs a power supply. It comes from the 12 volt ATX power supply. When all these conditions are met, the PWM driver will drive the high side MOSFET and the low side MOSFET by switching them on or off. and eventually it will go through this inductors, and then we have the VCORE of 1.0 volt, and this will go to the CPU. The output resistance is not that high, it's higher than 4 ohms. And also remember, this configuration is multiplied by 4 because we have 4 phases that will generate the VCORE voltage of 1 volt. This voltage is not present in the standby state and is present in the power on state. This is a small chip, and this is the PWM driver IC. The PWM signal that comes from the multi-phase PWM controller will go to this pin. Because we have in total 4 phases that generate the VCORE. In total there are 4 phases and we need 4 phase driver ICs. This PWM driver IC will drive a high side MOSFET and low side MOSFET. 2 MOSFETs will be used for the low side and 2 MOSFETs will be used for the high side. And then we have 2 chokes or inductors. From there it will go to the CPU. And this layout is multiplied by 4. So if we look at the layout, we see 1 phase here, 2 phase here, 3rd phase here, and the 4th phase here. So every phase has a PWM driver IC, and every driver IC is driven by this multi-phase PWM controller. And here we have a separate phase that is also driven by this multi-phase PWM controller. And this will generate a voltage for the graphic part for the CPU that is used by the integrated graphics. When the CPU core voltage of 1 volt is created successfully in the power on state, in the next step we have to create a VGT voltage. So this is a voltage that is used for the integrated graphics part in the CPU. And this voltage will be created after the CPU core voltage is generated. In region 32, the graphics core voltage is created. There's a PWM driver IC which gets its main PWM signal from this multi-phase PWM controller. So this is the master and it will drive the graphics core driver. And this PWM driver IC will start driving the high side MOSFET and the low side MOSFET, and it will provide the graphics core power for the CPU. So the principle is still the same. So in power sequence 32 we have to create graphics core voltage of 1 volt. In the standby state this voltage is not present, and in the power on state this voltage of 1 volt has to be generated. This is the PWM driver IC. It needs power to operate. It drives from the 12 volt ATX power supply. And this is the enable signal, and this comes from the PWM controller IC. This PWM comes from the multi-phase PWM controller. It will go into this driver IC, and this driver IC will start switching the high side MOSFET and the low side MOSFET. And in the output there will be a graphics core voltage of 1.0 volt present, and it will go to the CPU. And the resistance output is higher than 7 ohms. In power sequence 32 we need to create a graphics core voltage of 1 volt. In the standby state this voltage is not present, and in the power state it has to go from 0 volts up to 1 volt. This is the PWM driver IC that will start switching the low side MOSFET and the high side MOSFET. The PWM signal comes from the multi-phase PWM controller. It will go to pin 2. Then we need power on pin 3. Pin 18 and 13 will go to the high side MOSFET, and pin 10 and 11 will go to the low side MOSFET. And the enable signal at pin 15 comes from the multi-phase PWM controller. The reason why we have 2 MOSFETs for the low side and only 1 for the high side MOSFET has to do with the current. So most of the time the low side MOSFET is turned on and it has to endure a large current. So that's why there are 2 MOSFETs for the low side. And the high side MOSFET usually has to handle a lower current. That's why there's only 1 MOSFET in this case. And this is the output choke, so at the output there will be 1 volt present. PCH power OK signals are created in this region. In power sequence 33 we need to create a PCH power OK signal. PCH power OK is a status signal that informs the PCH, the platform controller hub, that the power to the system is stable and in acceptable ranges. It is generated by the multi-phase PWM controller that generates core voltage of 1 volt for the CPU. If that controller is operating correctly and the VCORE voltage is generated, it will send a VRM enable signal, a power good signal, and also the additional CPU voltages will send a power good signal to this chip. This is a logical AND gate, so if A and B are present, the output will be high. When the VRM enable signal is present, and the VRM is generating a core voltage of 1 volt for the CPU, that controller will send a VRM power good signal to to this line, and also the additional CPU voltages like the VCCSA will send a power good signal to this AND gate. At the output there is a PCH power OK signal of 3.3 volts. When these input signals are present at the input 1 and 2, the output Y will be high. So the PCH power OK signal will go from 0 volts to 3.3 volts in the power on state. PCH power OK is a status signal that informs the PCH that the power to the system is stable and in acceptable ranges. So basically only after the PCH power OK signal is present does the PCH proceed to its normal operation, managing the system's I/O, the PCIe devices, storage interfaces, USB and other peripherals. This chip is called a 2-input logical AND gate. This is input 1 and this is the input 2. Third pin is ground and this pin is the output. So at the output we can measure the PCH power OK signal and the output resistance is higher than 9 kilo ohms. So if the input 1 and 2 is high, the output will also go to a high state, and this is the PCH power OK signal. And this logical AND gate IC is located near the CPU. When the PCH power OK signal is successfully created, so it's high, the next step is to create the CPU power good signal. The CPU power good signal can be measured near the PCH. In power sequence 34, we have to create the CPU power good signal. It goes from low in the power on state to high, and it will go from the PCH to the CPU. This is the PCH and it will send a CPU power good signal to the CPU. And the output resistance of the CPU power good signal is higher than 20 kilo ohms. The CPU power good signal is a signal that is used to indicate that the CPU power supply is stable and within the correct voltage ranges. Only when the CPU power good signal is high does the CPU start executing instructions. Until this signal is received, the CPU remains in a reset or halted state to prevent damage due to the unstable power. This is a PCH and near this PCH there is a resistor. On the top side of this resistor you can measure the CPU power good signal that comes from the PCH, and on the bottom side you can measure the CPU power good signal that goes to the CPU. And the output resistance of those two signals is higher than 20 kilo ohms. And basically this CPU power good signal will go to the CPU. So in the standby state this signal is not present, and in the power on state it will go from low to high. And the signal goes from the PCH to the CPU. When the CPU power good signal is high in the power on state, the next step is to set the DRAM memory out of the reset state. So the DRAM reset active low signal has to go high because we want to get out of the reset state. The DRAM reset active low signal comes from the PCH and it will go to the DIMM sockets. In region 27 we can measure the DRAM reset active low signal. In power sequence 35 we have to create a DRAM reset active low signal. The DRAM reset active low signal is a voltage of 1 volt and will be created in the power on state. In the standby state this reset signal is low, and in the power on state it will go high because we want to get out of the RAM reset state. This signal is created by the PCH and it will go to the DDR RAM modules. So this is the PCH and the signal will come from the PCH and it will go to all the RAM modules. DRAM reset is used to reset the DRAM module, clearing any existing data or state within the memory cells and returning the DRAM to a known and initialized condition. The signal is typically asserted during the system power up sequence or when a memory controller needs to reset the memory during the boot or recovery process. The DRAM reset signal derives from the DDR power supply and it will create the DIMM reset active low signal. So this signal will go from low to high. So in power sequence 35, the voltage of 1 volt is present in the power on state, and it will go to every DIMM socket. In every DIMM socket, the pin marked in yellow is the DRAM reset signal, and it has to go up to 1 volt to get out of the reset state. When the RAM memory modules are out of the reset state, so this DRAM reset signal is high at the power on state, the next step is to release two important main reset signals. That is the platform reset active low signal and the CPU reset active low. there's a green checkbox here, and I put it there because this is the main reset signal. When this platform reset signal is low, it will reset different components on the motherboard, and it will remain in a reset state. In the power on state, the platform reset active low signal and the CPU reset active low signal has to go high. It has to go out of the reset state. The platform reset signal will reset different components and circuits on the mainboard, and the CPU reset signal will reset the state of the CPU. The platform reset active low signal can be found in area 28, and that's located near the SuperIO chip. The CPU reset active low signal can be found near the CPU at area 29. In power sequence 36, the platform reset active low signal has to go from 0 volts up to 1 volt. So in the standby state it has 0 volts, in the power on state it has to go high to 1.0 volt. And this signal comes from the PCH and it will go to the SuperIO chip. The platform reset active low signal is the most important signal because it resets different components and circuits on the mainboard. When this platform reset active low signal is low, somewhere in the circuit there is a problem and it will prevent from generating a enable signal or maybe some voltage. So then you have to troubleshoot which voltage in the sequence is missing. This is a PCH chip and there's a pin called platform reset active low signal. It will go through a resistor and from here it will go to the SuperIO chip. This platform reset active low signal is a hardware signal that plays a key role in resetting the platform, including the CPU, chipset and other components. The hashtag symbol indicates that the signal is active low, meaning it is triggered when the signal is pulled low at 0 volt, and it remains inactive when it's high. When the signal is high, the mainboard is not in a reset state, so the computer is ready for receiving and executing commands. This platform reset signal is used to initiate a platform-wide reset. It ensures that all major components of the system, including CPU, chipset and other peripherals, are properly reset and brought to a known initialized state. When this platform reset signal goes high, it indicates the end of the reset condition. The CPU and other components begin their initialization routines. The CPU will start executing the BIOS code, which handles the further boot process like memory initialization and loading the operating system. If the platform reset active low signal fails to work correctly, or if it remains asserted, the system will not boot or components like the CPU and chipset may not initialize properly. So in computer systems where the platform reset signal is stuck low, it may cause a no boot or a boot loop condition as the platform constantly stays in the reset mode. This is the PCH, and near the PCH there is a resistor, and at one end you can measure the platform reset active low signal. The signal has to go to a high state in the power on state, so it has to go from 0 volts up to 1 volt. And the output resistance is higher than 50 kilo ohms. And this platform reset signal that comes from the PCH will go into the SuperIO chip. And this is SuperIO chip, and this platform reset active low signal that comes from the PCH will go to this chip. And it can be measured at this pin. And at the same time, at power sequence 37, the CPU reset active low signal will also be created. So in the power on state it has to go from 0 volts up to 1 volt, and it will go from the PCH to the CPU. And this is the PCH chip, and at this pin the CPU reset active low signal will go high and it will go to the CPU. The output resistance of this output signal is higher than 1 kilo ohms. The CPU reset active low signal is responsible for putting the CPU in a reset state, which is used to initialize the CPU during the power on, rebooting or recovering from a certain system error. When this CPU reset signal is asserted, so it's pulled low, the CPU halts its operation and stops executing instructions, and is placed in a reset condition. During this time, the internal registers and execution units of the CPU are cleared or set to a default state. Once the signal is deasserted, so it's pulled high, the CPU exits the reset state and begins executing the instructions from the BIOS. During the system power up, the CPU reset signal is held low initially to keep the CPU in a reset state, while other components such as the power supplies and clocks stabilize. Once the power supply is confirmed to be stable and other critical signals like the power good are asserted, the CPU is released from the reset state by deasserting this reset signal. So the signal will go from 0 volts up to 1 volt. This is CPU, and the CPU reset signal that comes from the PCH will go through this resistor, and from here it will go to the CPU. And the output resistance of this signal line is higher than 1 kilo ohms. CPU reset signal that comes from the PCH will go to this CPU. When you measure the CPU reset signal and this signal is high, then you know that the motherboard is ready to start executing the instructions. And it also means that the whole sequence from standby mode up to power on mode is completed. And this reset signal indicates that all the power on voltages, all the standby voltages, all the enable signals, the power good signals that are generated in the previous sequences are present. All these voltages and signal lines are created successfully. Eventually this platform reset signal and the CPU reset signal has to be released. So it has to go out of a reset state, and these two signals will go high in the power on state. And now we have a fully working mainboard. So congratulations that you made it so far, and now you have a more basic understanding from which voltages and enable signals you have to measure to try to diagnose a problem on a mainboard. In the next slides I will provide some simple basic troubleshooting tips and also some information about resistances and voltages. So in this chart I have summarized all the voltage rails and signals with the correct voltages. I also provide the output resistances for these signal lines and voltage rails. This is a 24-pin ATX power connector that's located on the motherboard. These resistance values are measured for this specific mainboard. For different mainboards with different CPUs or chipset, these resistances are different. So this is just an indication when you measure the output voltages. For the 3.3 volt it's higher than 300 ohms. The minus 12 volt is higher than 3 kilo ohms. The power on pin is higher than 10 kilo ohms. The minus 5 volt has a high resistance value. The 5 volt has an output resistance of higher than 800 ohms. The 3.3 volt is higher than 300 ohms. Plus 12 volt is higher than 3 kilo ohms. The 5 volt standby pin is higher than 700 ohms. The power OK pin is higher than 2 kilo ohms. And again the 5 volt is higher than 800 ohms, and the 3.3 volt is the same as this one, is 300 ohms. Basically, if you measure a really low resistance, then there is probably a short on the mainboard. This 12 volt CPU power connector and a 12 volt output has a resistance of higher than 2 kilo ohms. If the ATX power supply is shorting or you hear a clicking sound, power down the power supply and remove the connector from the socket and try to power on the mainboard again. And if the mainboard is starting up, then you know there is a short on the CPU side. I made a list of the most common faults that you can see on motherboards. I will shortly go through them. So the most common symptom is a no post symptom, and it can have different reasons. First one, there can be a motherboard compatibility issue. So the motherboard BIOS doesn't support the CPU model. The cause can also be an incompatible RAM. So if the RAM is incompatible with the motherboard, the system may fail to post. The next is if you insert a new CPU but you didn't update the BIOS, you can have a no post condition because the BIOS version doesn't support the specific CPU that is installed. Next we have a RAM compatibility issue. Some BIOS version may not support certain RAM speeds, configuration or capacities. So it can also lead to a no post symptom. If a BIOS update fails, the BIOS might become corrupted and cause a no post condition. Also, a CPU damage can cause a no post condition, so bent or broken pins will cause a no post condition. And maybe there are damaged pads underneath the CPU. Overheating the CPU or improper installation of the cooling system might damage the CPU permanently, so a damaged CPU can cause a no post condition. Then we have motherboard damage, like the bent socket pins where the CPU is inserted. It can cause a no post condition. The motherboard itself can have a correct PCB board, so the data lines will not go through the copper lines. Then we have the damaged tracer or components on the motherboard. We have to look for burn marks, missing capacitors, damaged traces. All these damages can prevent a no post. Short circuits on the motherboard will also cause a no post condition. Damaged contacts on the RAM module or dirt and debris in the DIMM slot can prevent proper communication, and that will prevent the motherboard from posting. The RAM can also be damaged by physical stress. Forcing the RAM into the slot the wrong way or improper handling can damage the modules or the motherboard slot, and that will cause a no post condition. If the motherboard is booting up, Check if the LEDs or caps lock, num lock LEDs can be turned on or off by pressing it on the keyboard. If the LEDs on the keyboard are not responding, they can conclude that the mainboard is not responding to any commands that comes from the keyboard and that the mainboard is not responsive. To analyze no-post conditions, we use a post card analyzer to see if there is any communication with the BIOS and the PCH. With this post card analyzer, you can identify hardware problems when a computer fails to boot or display error messages, so it will give an indication where the problem lies. On high-end motherboards, there are LEDs on the motherboard that can indicate a fault. A debug LED on a motherboard is a built-in diagnostic feature that provides a real-time feedback during the power-on self-test. With the debug LEDs, it helps identify hardware issues that prevent the system from booting correctly. And sometimes you can also see the error codes on the motherboard. So this will help you to find the problem area and troubleshoot the mainboard. If you see a blue screen or the operating system hangs, it may indicate that the BIOS is corrupted, and then you have to reflash the BIOS. If you measure the standby current and it is very high, it indicates a problem. If you have a high standby current, you have to try to eliminate which component is causing the problem. You can remove the CPU or the RAM modules and measure the standby current again. If the current is still very high, it may indicate a short on the mainboard. When you press the power button and the system doesn't react, then you have to check the output inductor that supplies power to the PCH and measure this resistance. If this resistance is low, check if the PCH is shorted by measuring the caps on the PCH. Also check if the PCH chip is not correct or damaged, because if this voltage is missing, the trigger to power on will not be processed by the PCH chip. When you press the power button and the power supply is shorted or it gives a clicking sound, then remove the 8-pin CPU connector and try to power on the mainboard again. And if the short is removed, then you know the short is on the CPU side. When the computer is crashing on a load, it can be caused by a BIOS that is not supported by the CPU. Also, you have to update the BIOS. It can also be caused by missing capacitors on the mainboard. And also the used components that are on the board could be incompatible, so they can also cause a crashing on the load. When the settings for overclocking the RAM memory are not correct, it can cause a crashing on the load, and the same is for overclocking the CPU. Always check if the BIOS is up to date. You can stress test the PC with the Limpack Extreme software, Firmmark or Heaven benchmark. With this software, you can stress test the PC at a high load. Also check your CPU temperatures with CPU ID. When the CPU core voltages are high, it will crash the system. You can also test the motherboard by hitting it softly with your hands and see if the motherboard is unstable. The cause can be a cold solder joint, then you have to reflow the solder joint. When you have a stock debug CPU LEDs without postcodes, it can indicate a BIOS firmware problem, or maybe there are some components missing on the mainboard. When the BIOS firmware is faulty, you can check if there is a connector near the BIOS IC. When this connector is present, you can flash this BIOS IC in circuit. Check if the platform reset active low signal is missing. And if this signal is missing, then you have to check the 2-input logical AND gate, because the output of this 2-input logical AND gate depends on the input. You have 2 input signals that has to go high before the output is generated. If the output signal is missing, it can pull this platform reset active low signal to ground. With all the active low signals, you have to check if there is a 2-input logical AND chip and check if the input signals are present and the output signal is present. If you want to flash the BIOS IC that is located on the mainboard, you can use this programmer, the CH341A. This programmer is a USB to serial interface chip that is used for SPI, I2C and UART communications. It's commonly used as an EEPROM and SPI flash programmer, making it useful for BIOS flashing, firmware recovery and debugging embedded systems. In this case, this programmer is used to flash BIOS ICs. I will not explain how to flash the BIOS, because there are enough videos on YouTube where you can learn how to use this device. The most important to know is what kind of voltage does the BIOS IC uses. Here are 2 BIOS ICs from Winbond. The one uses 3.3 volts and the other one uses 1.8 volts. There's a little trick. After the F there is a W, Then this is a 1.8 version, so the power supply to this chip is 1.8 volt. If the W isn't after the F, then this BIOS chip uses 3.3 volt. This 2-input AND gate IC is a digital logic chip that outputs high only when both inputs are high. Otherwise, the output will be low. This chip is used in circuits for decision making, signal control and logic operations. If the output represents a signal line like platform reset, CPU reset, a PCH OK signal, and this signal depends on other signals to be present like enable signal and power good signals, this chip is used. When the output signal is not present, then you have to check this chip if it is working correctly. You have to check the power supply and also the input signal if they are present. If both are present and they are both high but the output is low, then you can conclude that this chip is faulty. When you have RAM problems, first one, you check the data lines between the DIMM slot and the CPU to check if the data lines aren't broken. Also check for broken and missing components near the DIMM slot, and also on the memory module. The data lines from the RAM module will go directly into the CPU. So check if the CPU socket is clean and okay, and also check if the DIMM slots are clean. Next is to check if the power supply for the memory is present, and also if the VTT voltage rail is present. Check if the voltage regulator works, if the output voltages are generated successfully. When this RAM module is not detected, it can be a cause of a missing voltage, and maybe the RAM is not supported by the BIOS. To check if the motherboard has RAM problems, you can connect a speaker on the motherboard, and if it beeps, this can indicate a RAM problem. To analyze the standby current, you can use this module. This is an ATX connector with a built-in voltage regulator. You have to connect the plus and minus wire to your lab power supply. Then you have to set the power supply to 12 volt. And when you turn the power supply on, then you can monitor the current. When the current is high on the lab power supply, this can indicate a short on the mainboard. On the mainboard, the standby current should be around 300 milliamps. It depends on how many RGB LEDs are on the mainboard, so it can sometimes be high due to the LEDs. If there aren't any RGB LEDs present, then the current should be around 300 milliamps. When this 24-pin ATX voltage regulator is connected to the lab power supply and you power on the mainboard, the current should be jumping between the 2 amps and 7 amps. If you see a steady current, it can indicate a problem on the mainboard. Always remember, before connecting any device on the mainboard, measure if there aren't any shorts on the voltage rails. Then you will destroy this voltage regulator. This is a DDR5 memory slot tester, and with this tester you can test the data lines that will go to the CPU. Also the CPU should be inserted, and when you press this button, all the data LEDs should be turned on. If the LEDs of some data lines are not lit, it could indicate a problem because the communication cannot be done between the DIMM slot and the CPU. So this tool is just an indication, it will not give a 100% certainty that it is okay. This is a diagnostic analyzer. This is the TL631 Pro. This analyzer includes several LEDs indicators to help diagnose any issues with different computer components. You can connect this analyzer to a PCIe Express slot, and it can also be connected to a PCIe connector, an LPC2 normal connector, and an LPC1 mini connector. And you can also connect the LPC from the laptop with a ribbon cable to this connector. With this analyzer you can show the postcode, you can show the clock signal and the frame signal. The frame signal is used by the LPC protocol. You can also see the debug LEDs. If there aren't any postcodes, it will display 00. With these LEDs, you can diagnose the motherboard. The first LED is a 3-volt standby power indicator. So this confirms if the standby power is functioning. So this LED is on. Then we have the motherboard reset signal. And if the motherboard is in a reset state, this LED indicator is turned on. In a normal situation, this LED has to be turned off. Next we have the CPU indicator. So this checks the state of the CPU. In a normal situation, this LED has to go off. Then we have the DRAM indicator. It verifies the functionality of the RAM modules. and in a normal situation, this LED has to go off. Next we have the graphics card indicator, and normally this LED has to be turned off. If there are any issues with the graphics card, you will see this LED will be turned on. Next you have the PCH indicator, so it will test the solid bridge and the chipset module. In a normal behavior, this LED has to be turned off. Next we have the clock signal and the frame signal at these LEDs, and these LEDs will start blinking if there is activity. And the postcodes are shown in this area. The postcodes are only shown when the BIOS is initialized and the self-test starts. On modern motherboards, they have a LPC connector, and we can connect this diagnostic analyzer to the LPC connector on the motherboard. So if we look at the PCH chip on the motherboard, and the PCH chip has LPC pins, so it supports the LPC protocol, the low pin count protocol. And these data pins, the frame pin will eventually go to a TPM header. And on this TPM header, you can connect the analyzer. You can connect this analyzer to the TPM headers. The LPC bus was introduced by Intel as a replacement for the older ISA bus. The LPC bus is designed to connect devices that do not require a high-speed data bus, like the BIOS, the SuperIO chip, the TPM, the Trusted Platform module, also the embedded controllers. The LPC 0, 1, 2 and 3 are the data lines. The L frame is a frame signal. It is used to indicate the start and the end of a transaction. This is an interrupt pin. It allows the LPC device to send interrupt request signals to the CPU. By connecting the analyzer to the TPM headers, we can read the BIOS codes that comes from the PCH chip. Also, the SuperIO communicates by the LPC bus. This is the SuperIO, and the LPC pins are located in this region. And these pins will eventually be exposed to the TPM headers. So the analyzer will be connected to this TPM header. Before connecting the analyzer, always locate the pin number 1. It's indicated by a mark on the silk screen. Near the PCH, this interrupt signal can also be measured at a resistor. Every motherboard uses a different TPM header or LPC header. Some use a small pin LPC interface, and other motherboards uses a bigger LPC interface. If you see these headers on the motherboard, always locate pin number 1. If this is the diagnostic analyzer, locate pin 1 and connect it to the pin 1 of the TPM header. Sometimes you have a long TPM header, but you always have to connect it to pin number 1. Here you can see different TPM headers from different motherboard manufacturers. This mark on the silk screen is pin 1. This arrow is pin number 1. This is pin number 1. This pin number 1. So here we have a mark, so this is pin number 1. So now you know how to connect the LPC analyzer to the TPM headers on the mainboard. Here's a short description what each of this LED means. And that's it for our 3-part series on the power sequence of desktop motherboards. We have covered everything from the RTC clock to the standby power and the power on state. If you found this series helpful, hit that like button, subscribe and turn on the notifications. Thank you for watching, and I'll see you in the next one. Till then, bye bye.